We're going to take a look at an application of working with Heaviside functions in modeling differential equations. So this one, for a drug utilized in emergency hospital settings such as morphine, doses are extremely critical. It is known that morphine has a half-life of 1.5 to 7 hours and that a concentration of 2 milligrams per liter is likely in a setting involving anesthetics, including any situation involving incisions and or surgery that would normally be painful. So there's a source for that. And so we're just going to go ahead and assume a half-life of about 4 hours for a person with 5 liters of blood. That would mean that about 17% of the amount of the drug is filtered out of the bloodstream each hour. Assume the following: 7 milligrams will be added continuously over the course of an hour. This will be done for 1 hour, at which time the dosage will be adjusted to 4 milligrams. Okay, so in order to model something like this, we first of all just have to think about the dependent and independent variable first. So we're going to let y be the amount of morphine in blood. In milligrams, and t will be I guess we'll just say after t hours. And so what we know is that at all times, and I'm going to write a piecewise function because we know that the infusion rate changes, there's always going to be a exiting, if you will, of 17% of the amount of morphine in the bloodstream each hour. So that is in units of y over units of t. That is in milligrams per hour. That's what's leaving the bloodstream no matter what you give it. At time 0, we're going to be infusing 7 milligrams per hour. So that's 7 milligrams per hour. And that's going to be done for 1 hour. So that will be for t less than 1. Now, if you notice, I'm not putting the boundary of 0 on here because it's just assumed that we're dealing with positive, or rather non-negative values of time. And so next at this point, we want to have 4 milligrams per hour. And that will be for t greater than or equal to 1. Now, in order to model this with a Heaviside function, and of course y of 0 is equal to 0 because we're assuming that we're just beginning the infusion process. So we need to be able to somehow switch this from a 7 to a 4. And that's just a constant. So there's a couple of ways that I could do this. Here is the way that I think I will go ahead and choose to do it. I will think about 7 as really just being 4 plus 3. And the reason that is because notice that the 4 will remain intact. The only difference is we'll have plus 3. And furthermore, I'm going to think about this as 4 plus 3 times 1. And I'm going to think about this one down here as 4 plus 3 times 0. See, what I'm trying to do and this is not by any means the only way to represent this. You could think about turning on the 7 and then turning it off. And then you could think about turning on the 4, and that would work perfectly fine as well. But this allows me to just worry about one term instead of having to, figure out how to make a 7 become a 4. If I represent it as 4 plus 3 times 1, then I'm going to build a little t-table here. I know time 0, 1, 2, 3, 4. I know this is going to involve a Heaviside at time 1, which naturally would be a 0 until you hit time 1, and then it would be a 1 forever. Now, here is what I want. Here's my desired. I want the 3 times 1 to be in effect until we hit time 1, right? And then what I want is for that term to become a 3 times 0. I'm just thinking about the 3 piece because the 4 is before time 1 and time 1 or greater. Same thing with the negative 0.17y. So I have to ask myself, how could I combine the U1 with in order to produce the desired? Well, here's the thing. When Heaviside is 0, I want a multiplier of 1. And when U1 is 1, I want a multiplier of 0. So how could I possibly manipulate change a 0 into a 1 and change a 1 into a 0. And here's the trick. If I do 1 minus u1, okay, I'm going to do this off to the side. 1 minus u1 would look like this. As a piecewise function, for time less than 1, you would have 1 minus 0. Because all I'm doing here is I'm plugging in 0 for u1. For t greater than or equal to 1, this would be 1 minus 1, which is 0. So if you do 1 minus the Heaviside, you flip the 0 into 1 to become 1 and 0. And so if I take 3 times this, well, depending on whether time is less than 1 or greater than 1, this will be 3 times 1, and then 3 times 0, 3 times 0, and so on down the line. So with that said, our answer for part A is that our differential equation should look like this. dy dt equals, I will write it as 4 plus 3 times the Heaviside, 1 minus u1, minus 0.17y. Initially, nothing at all in the bloodstream. So you can pause and verify that this differential equation gives me exactly what we want. When time is less than 1, this piece is 3 times 1, which is 7. 4 plus 3 is 7, minus 0.17y gives me what I expect. When time is bigger than 1, then 1 minus the Heaviside becomes 0, and we get 4 plus 3 times 0 minus 0.17y, which is exactly what we have down here. Let's go ahead and solve this Heaviside. So I'm going to begin in exactly the same way we've done with Heaviside, with Laplace transforms, and take the Laplace of both sides. But I think what I'm going to go ahead and do here is I'm going to distribute to make this 4 plus 3 minus 3u1 minus 0.17y. And you do see here, it actually does end up giving us 7 right here, but then I have 7 either minus 0 or 7 minus 3. I guess we could have just fabricated it this way as well. We could have just said that this term needs to be 7 minus 3u1. Maybe that would have been an easier way to think about it, but this works as well. So take the Laplace of both sides. Laplace of a derivative is s times the Laplace of y minus the initial condition. That equals 7 minus 3 times the Laplace of the Heaviside is e to the negative as, which is negative 1s over s, minus 0.17 times the Laplace of y. So as always, we need to get this over to the other side. We'll have s minus 0.17 times the Laplace of y. You're like, what are you doing there? Well, if you add over the 0.17 Laplace of y, you'll have 2 terms involving Laplace of y, s Laplace of y, and then plus 0.17 Laplace of y, and then you factor out a Laplace of y from that. This, by the way, gives us 0, because that's our initial condition. And now the, oops, I didn't take the Laplace of 7. The Laplace of 7 is 7 over s. And so we get 7 over s minus 3e to the negative 1s over s. Excellent. Divide so that we isolate L of y. We get 7 over s times s plus 0.17 minus 3 e to the negative s. I'm going to keep the 3. I'll choose to keep the 3 in the numerator because I'm going to need to do a partial fraction decomposition here. S over s plus 0.17. All right, so I actually need 2 partial fractions. I need a partial fraction here, and I need a partial fraction here. So I'm going to go ahead and do that and see what we come up with. And the partial fraction decomposition of 7 over this stuff is 41.18 over s minus 41.18 over s plus 0.17. Now for this second piece here, notice that I just said the partial fraction decomposition of the 3 over. We don't want to incorporate this in there because if you try to do that with most technology, it's not going to be able to parse it up. So what I'm doing is I'm just taking this piece right here and then writing its partial fraction decomposition. Now, as you guys can see, we already know that this guy's inverse will be 41.18. That's the Laplace of a constant. This will be negative 41.18 e to the negative 0.17t. The trouble I'm going to have here, or I shouldn't say trouble, but the challenge before I can do anything is I need to distribute that back in. And I'm going to write it like this. E to the negative 17.65 e to the negative s times 1 over s. And then I'll get a positive here because I'm multiplying a negative, negative with a negative. 17.65 e to the negative s times 1 over s plus 0.17. And the reason I'm writing that, we already know these guys' inverse. We'll come back to these. We're going to need those two terms. We're going to focus on this. This is the second Laplace transform that we have in our new transforms, where what we have is we have e to the negative 1s multiplied by the Laplace of some unshifted function. So we have to ask ourselves, so because we have that e to the negative s term right here, we know that this second factor, the third factor in this multiplication sequence, that this is the Laplace of some function. So what function is that the Laplace of? Well, that would imply that f of t is equal to the constant 1. Because that's the Laplace of, is the constant 1. And the a value that I have here is equal to 1. The a value should always be equal to 1 because notice in our model we started with u1. And so that was precisely what we wanted. Now here, we have to ask ourselves the same thing. What is this function, the Laplace? Well, again, a is 1, and f of t is equal to e to the negative 0.17t. Okay, so that gives me what f of t is and what a is. Now, in order to invert that, that's going to end up being u sub 1 of t times f of t minus 1. So basically, working backwards, I have to shift it a units, each of these functions a units to the right. So I have to ask myself, well, what is f of t minus a? And normally what we would do is we would replace all the t's with t minus 1. But here there is no t in it, right? It's the constant function 1. So if you think about what that looks like, that is just the horizontal line. And if you shift it 3 units, it's still just the exact same function. So the shift 1 unit to the right doesn't affect this function here. Now, over here what we have is again, a equals 1. So we need to know what is the shifted version of this. And now all we have to do is replace t with t minus 1. So negative 0.17 t minus 1. Awesome. So we are pretty much ready to do the inverse Laplace here. So I will just write y equals, we already know the inverse Laplace of 41.18 over s. We know the inverse Laplace of negative 41.18 over s plus 0.17. Now for this piece here, this is going to be u sub 1 of t, a equals 1, times f of t minus 1, which is 1. But keep in mind that we had the negative 17.65, so we have to put that there as well, minus 17.65. This was positive on this side, so I'm just going to, before I forget, copy down that 17.65 right there. A is equal to 1 again, so the inverse of this is u sub a of t times f of t minus a. E to the negative 0.17 times quantity t minus 1. Perfect. So there's our solution, my friends. We are one step closer. Notice that at no point in time did we have to work with any of the discontinuities other than to grapple with the Heaviside functions, but we did not have to solve this equation in pieces. We solved it as one solid problem. And now when we go to graph it, we will actually incorporate these Heavisides, and I'll go ahead and show you how to do that. The question here is, using graphical support of the solution, will the amount of drug reach the desirable level so that surgery can take place at the 2-hour mark? Well, I've already written it up here. We know that in a setting like this, 2 milligrams per liter of the anesthetic is what we need. The person that we're dealing with has 5 liters of blood, so 2 milligrams per liter times 5 liters, we're gonna need a desirable level of 10 milligrams when we go and assess this. So let's go to Desmos. Now, to get a piecewise function in here, it's pretty easy. I'm going to call it u sub 1, u underscore 1, just so that I know what we're referring to here, of x equals, but I mean, you could call it anything you want. You can call it w of x if you want. The fact that we're using a u tells nothing to Desmos. That's just its name. Now, in order to do a piecewise function, which this close curly bracket, and the first thing we do is we say, for what interval? Well, for x less than 1, and then a colon to tell it, all right, what do you want for x less than 1? Well, the function that we want for x less than 1 is 0, because that's the definition of the Heaviside. And then comma, for x greater than equal 1, we want the function colon to be a 1. And as you can see here, we get that function, right? In fact, it's going to define it for all the negatives as well. We're just not going to focus on anything less than x, well, in our case, t less than 0. But you notice here that at time 1, if I try to click on that point, it actually bounces up, jumps up to the point 1, 1, because we said for x greater than or equal to 1, we want the output to be a 1. Now all we have to do is put in the rest of the function. So in our case, I'm going to call this g of x equals 41.18 minus 41.18 e to the negative 0.17x. And then I think we had minus, what was it, 17.65 times u sub 1 of x. So now I'm referencing this function, which is defined up here. So that's how it knows what it's doing. And then I need plus 17.65 times u1 of x multiplied by e to the negative 0.17 times quantity x minus 1. Now I'm going to get rid of the Heaviside because I'm not really interested in that. And let's kind of see what happens here. And as you see, hopefully you can see this, that the function has a very steep rise and then it sort of flattens out a little bit. And why is that happening? Well, at this point, this represents, on the vertical axis, we are looking at y, the milligrams of morphine in bloodstream. Y-axis is time, t, which is time in hours, I believe, right? Yeah, time in hours. And we know that at time 1, this interesting thing takes place. So I'm going to take a look at this from, we're going to say 0 to 11, because I want to know, does this reach 10 in time? And now I'm just going to go from, maybe x goes from 0 to 3. I don't need to go farther than that because I'm really just interested in what happens at the 2-hour mark. So notice we're infusing at a certain rate. This is going to be at a rate of 7 milligrams per hour. But then at time 1, we decrease the rate of infusion to only 4 milligrams per hour. So the body is still processing this out, but because I'm pumping it in at a slower rate, the rise of morphine in the bloodstream takes place at a slower rate. Now I can graph the line x equals 2 to see where we are at the 2-hour mark, and we can see that we don't hit it. We don't hit the desired benchmark. So either we could wait a little bit longer before surgery starts, up until almost 2.5 hours, right around there somewhere, 2.39, 2.4 hours, or we could try to increase one of the infusion rates. So there we go. There's a full model of this problem.